In this video, we'll take a look at some specific examples of infinite limits and some of the methods that we can use to evaluate them. So let's look at, let's make a list of examples here. And let's start with this one. So let's say we have the limit as x approaches -2 from the positive side of 2x plus 3 over x plus 2, and then we will also look at the other one-sided limit. So the limit as x approaches -2 minus of 2x plus 3 over x plus 2, and then we can finish it off by looking at the two-sided limit, right? And just something to note, in a lot of these questions, you'll know when you are given a two-sided limit, depending on what happens when you try to use one of our algebraic methods, you might realize that, hey, I have to go back and check the one-sided limits anyway, right? So let's go ahead and do these in order. So let's take the limit of the numerator. So the limit as x approaches -2 plus of 2x plus 3. Well, that's a simple linear function. So we can evaluate it at -2. So that's 2 times -2 plus 3. And that comes out to be -4 plus 3, which is -1. Okay, so the numerator approaches -1. What about the denominator? So now let's look carefully at this. So the limit as x approaches -2 plus of another linear function. The problem though with this linear function in the denominator is that when I evaluate it at -2, I end up with 0. So this form is, it's not a number, right? It's -1 over 0. But what does that mean? Well, this is the clue that it's one of our infinite limits. So we essentially have three possibilities in total: either -infinity, +infinity, or does not exist. Right? So how do we decide? Well, the fact that it's a one-sided limit, now this is telling me that x is getting closer and closer to -2, but is slightly bigger than -2. So, so when x is bigger than -2 and close to -2 and close to -2. Look at what happens if I simply add 2 to both sides. So then x plus 2 is greater than 0. So what that means is the denominator is getting small, but with positive values. So what I'm going to do here is I'm going to indicate that this is a 0 plus. Right? So when we put this all together, what does this mean? It means that the limit as x approaches -2 plus of the rational function 2x plus 3 over x plus 2, I'll put this in quotes, it's -1 over 0 plus. So you're taking so your numerator is approaching -1, but your denominator is approaching 0 from the positive side. So the net result will be something negative, and it will be negative and very, very large. Hence, the answer is a -infinity, right? So what we have to do essentially to distinguish between a plus or minus infinity, we have to look at the signs of the numerator and the denominator and see if they're positive or negative, and then think about what happens when you do the division. So if you're taking a number that's getting closer and closer to -1, but you're dividing it by a number that's getting closer and closer to 0 from the positive side. So the net result will be a negative large number. All right, so that's the limit from the right. What about from the left? Well, from the left, this is still true, right? So as you approach -2 minus, and then you have your linear function 2x plus 3, that's still equal to -1. However, in the denominator now, right, if we take, so what we can say, this is saying, excuse me, that your x is less than -2 and close to -2. If that's true, then what's in the bottom, x plus 2, will now be less than 0. So what we end up having is this. So the limit as x approaches -2 minus of 2x plus 3 over x plus 2. This, and again I put this in quotes, the numerator still approaches -1. The denominator still approaches 0, but it's now from the negative side, right? Because if you start with the value of x that is less than -2, then x plus 2 would have to be a negative number. So what we end up having now is essentially something approaching -1 divided by something that's getting very, very small but negative. So those two negatives make the quotient a positive infinity. So you'll get a large positive y value, right? And then, so what do we say about the two-sided limit? Well, the one-sided limits are not the same. We won't say like they're not the same number, because we know that infinity and negative infinity, those are not numbers. However, the function is approaching large negative numbers here, large positive numbers here. So the two-sided limit does not exist, right? So does not exist, right? So what it comes down to, again, is recognizing when you have one of these forms, right? You have a non-zero number divided by 0. You have to decide, is it 0 plus positive numbers approaching 0, or is it 0 minus, where you have negative numbers approaching 0? All right, let's do another example with, let's say, something like this. Now, let me do something, just change our first example just slightly. So let me take just 2 over, and then what I'm going to do is I'm going to take x plus 2 and then raise it to the 4th power. Right? Now in this case, if you notice, so this has the form, even if I were to plug in -2 right now to try to evaluate it, right? So the limit of the top, since the top is a constant, the constant never changes, right? Look at the bottom. So the limit as x approaches -2 of the quantity x plus 2 to the 4th power. Well, that's -2 plus 2 to the 4th power, which is 0 to the 4th power, which is 0. And the interesting thing is, so you might say, well, what happens when you're close to -2? Well, it doesn't matter from the left or from the right, because the denominator has something raised to an even power, right? So what I'm going to say is this. So for all x not equal to -2, x plus 2 to the 4th power is always positive. So as I get close to negative 2, whether it's from the left or from the right, and that's why I have this not equal sign is basically saying, what if I am either on the left or on the right of negative 2? Well, if I do this operation, it will always result with something that's positive but small. So technically, this is 0 plus. And what that means is this infinite limit. We know it's infinite limit because we have a non-zero number in the numerator and then we have 0 in the denominator. But this is now 2 over 0 plus. So a positive 2 divided by a small positive number gives me a positive infinity as that number continues to get smaller and smaller and smaller, right? And incidentally, what would happen is if you were to look at the graph of this function, it will look like this. So it will have a vertical asymptote at negative 2. So over here, this will be x equals negative 2. And on either side, you will see this positive infinity from the left, positive infinity from the right. So that's what happens when you end up with basically the denominator being always positive, right? Or sometimes it could be always negative, and then the function would be going down on both sides of the vertical asymptote. All right. Let's try one more example. Let's look at a slightly different type of function. So let's take the limit as x approaches pi over 2, let's say minus of our, let's take the secant function. So let's take secant of x, that one, and then let's also look at the limit from the right of secant of x, and then finally let's put it together and answer the two-sided limit. So secant of x. Alright, so now let's start with this one. Now the first thing is you look at secant and it doesn't look like it will give you like 1 over 0 or 2 over 0, but we can rewrite this. Remember the definition of secant is 1 over cosine. Right, so this is 1 over cosine. And what happens is as x approaches pi over 2, so let me just talk about the number first, right? So we can see that the limit as x approaches pi over 2 minus of 1, well, that's going to be 1. So the numerator will be 1. The denominator, what does that approach, right? So let's do our pi over 2 minus cosine of x. Well, if you plug pi over 2 in, right, cosine of pi over 2 is 0. So we do have our form for an infinite limit. The question is it 0 minus or 0 plus? For trig functions, this is where our unit circle is really, really helpful. So I'm going to draw the unit circle down here, or at least a portion of it. And remember these rays, this one here, corresponds to 0, this one to pi over 2, this one pi, assuming we're going counterclockwise, and then down here 3 pi over 2. Now let's think about it for a second. X is approaching pi over 2, so that means I'm approaching due north. But my value of x is just slightly less than pi over 2. And based on how we measure angles, then it means that that angle would have to have its terminal ray would have to be in the first quadrant, like this would be x. And what's happening is this x is getting closer and closer to pi over 2. So in the first quadrant, we know that x would be between 0 and pi over 2, and the cosine of x would be a positive ratio. So then this would be 0 plus. Right? So what does that mean? Well, it means that this infinite limit is, again, I'll put this in quotes because this is not a real number. It's not a well-defined expression. 1 over 0 plus, that's positive infinity, right? Numerator, that's approaching 1. Well, it's always 1 since it's a constant. And the denominator is approaching 0, but with positive values, right? Well, what about the limit from the right when you're bigger than pi over 2? Well, bigger than pi over 2 means that your coterminal array is right here, and then this would be your x. And then the ray is coming back this way. So whenever your x is just a little bit bigger than pi over 2, but getting closer and closer to pi over 2, then I'm just gonna write down the expression for the bottom. So the limit as x approaches pi over 2 plus of cosine, it's still going to approach 0, but now in the second quadrant, cosine is negative, right? So the denominator is going to be 0 minus. That means, when we put it all together, the limit as x approaches pi over 2 plus of 1 over cosine x, that is 1 over 0 plus. So again, the 0 plus here is indicating a small positive number, and then so 1 divided by a small positive number is a large. Oh, I'm sorry. This is 0 minus, not plus. There we go. So 1 over 0 minus, and then this is negative infinity. Right? And then what happens is, again, the two-sided limits are different. They're not the same. These represent large positive numbers. This represents large negative numbers. So the two-sided limit does not exist. Right? So what it comes down to is when using algebra to determine whether an infinite limit is plus or minus infinity, we have to look, first of all, we want to have a ratio where there's a non-zero number in the numerator and then 0 in the denominator, and we decide if we're approaching 0 with positive numbers or with negative numbers. That helps us to distinguish between the two. Right, so hopefully you found this helpful and informative, and I'll see you in the next video.